Now that we understand the idea of a vector and how it relates to a matrix, we want to talk about basic vector operations like adding, subtracting, and multiplying vectors. And of course, because vectors can be written as matrices, this is going to look really similar to adding, subtracting, and multiplying matrices. So when it comes to vector addition, let's say that we want to add two vectors. We'll take the vector -1, 2, and the vector 3, 4. If we want to add these vectors, as you would expect, this is just a matrix addition problem. So we simply add across corresponding entries. So -1 plus 3 is a +2, and 2 plus 4 is a +6. And so the sum of those two vectors is 2, 6. The difference of the two vectors, if we subtract them, so if we start with -1, 2, and then we subtract the vector 3, 4, just like subtraction with matrices, we just find the difference of corresponding entries. So we say -1 minus 3 is a -4, and 2 minus 4 is a -2. And so the difference is -4, -2. Now when it comes to vectors, we want to understand this graphically as well. So the most interesting thing is that when we start with the first vector, so -1, 2, let's go ahead and sketch that in. So in standard position, we would have the vector -1 and then up to +2. So it would look something like this. And then if we have the vector 3, 4, we could sketch it in standard position as well. So let's go ahead and do that first. So in standard position, 1, 2, 3, and then 1, 2, 3, 4, looks like it's about right there. So we have the first vector, -1, 2, and then the vector 3, 4. When we add vectors together, what we're really saying is that we are connecting the initial point of the second vector to the terminal point of the first vector. And so we move the vector 3, 4 to connect it to the end of -1, 2, and then the sum will be the vector that connects the initial point of the first vector to the terminal point of the second vector. And we can see that. So if we sketch in 2, 6 in standard position, we get a vector that looks like this, 1, 2, and then up to 6, looks like it's about right there. And we can see that we get the vector that connects the beginning of -1, 2 to the end of 3, 4. And we can do this in the opposite way as well. Remember that matrix addition is commutative, so vector addition is commutative. We could start with the vector 3, 4. So let's say we start with that in standard position and we go out 1, 2, 3 and up to 4. So that might look something like that, 3, 4. And then if we add to that the vector -1, 2, and we started at the terminal point here of the first vector, we're going to end up with a vector that points us to 2, 6. So it doesn't matter in which order you add the vectors, you're still going to get to the same result. And that's what adding vectors looks like graphically. When it comes to subtracting vectors, remember that matrix subtraction is not commutative. So we can't take 3, 4 and then subtract off -1, 2. The order matters here. We have to say -1, 2 minus 3, 4, which means we want to start here with the vector -1, 2. So let's say that we start with -1 and then +2 coming up here. And then we want to subtract 3, 4. Well, normally the vector 3, 4 would move off in this direction, 1, 2, 3, and then up to 4. And the vector would look something like this. This would be the vector 3, 4. And so if we wanted to add the vectors, we would go ahead and connect that to the terminal point like we did last time. But when we're subtracting a vector, we take the exact same vector, but we move in exactly the opposite direction. So we rotate it 180 degrees, or we move in the opposite direction. So instead of moving off to +3, +4, we could start at the origin and move off 1 to -3 down to -4, somewhere right about here. So this is what it would look like to subtract 3, 4. And you can see that the result is -4, -2. So if I sketch that in standard position, I get -4 and -2. I didn't do a super good job drawing this, but it comes out to the same spot as where I got to when I started with -1, 2, and then subtracted away 3, 4. In other words, took 3, 4 and went in exactly the opposite direction. So again, if I sketched out this vector here, what I can say is that this vector here is adding 3, 4, and that this vector here is subtracting 3, 4, moving in the opposite direction. But both of them are starting at the terminal point of -1, 2. And you can see that when I add, I get to the result 2, 6, which we found here. And when I subtract, I get to the result we found here, -4, -2. So that's what vector addition and subtraction looks like graphically. And then the only other thing that we want to know is vector multiplication. And there are actually different kinds of results we can get when we multiply two vectors together. But the simplest and most basic one, the one that we want to focus on right now, and we'll actually learn a lot about it and other vector products later, is called the dot product. And the dot product just says that if you have two vectors, so let's call this first vector -1, 2, let's write it this way as the vector A is equal to -1, 2. And then let's call the vector B 3, 4. So let's say B is the vector 3, 4. Then the dot product just says that the product of A and B, and here's what the dot product looks like. We put this little dot in between the two vectors, that's going to be equal to the product of the first components of each vector. So we take the first component here, -1, and multiply it by the first component there of 3. So we get -1 times 3. And then we add to that the product of the second component. So in this case, 2 and 4. So we multiply there and we get 2 and 4. And then the result of that is, of course, -3 plus 8, and we get +5. And so the product of A and B, specifically the dot product of A and B, is 5. If we want to find the dot product, but we want to express the vectors A and B as matrices like we have up here, that's fine, but we have to express one of them as a row matrix and the other as a column matrix, and make sure that we multiply the row matrix by the column matrix. So for instance, if we call this vector A, let's say we call it matrix A, and we call the vector B matrix B, then if we want to find the dot product, we multiply those matrices. We can say A times B as if we were multiplying matrices. But the first matrix has to be a row vector. So we have to take the vector -1, 2, the vector A, and we have to make it a row vector or a row matrix. So it looks like this, -1, 2, and then the second vector, B, has to be the column vector or the column matrix. And the reason is because the dot product has to come out as this real number value. It has to come out like a scalar. It can't come out as another vector or a matrix, which means that the result of this product has to be a 1-by-1 matrix so that we end up with one value. And the only way to do that is with our dimensions that we set up here, because this row vector is now a 1-by-2 matrix, and this column vector is a 2-by-1 matrix, which means the product of A times B will be a 1-by-1 matrix, which is just like the scalar of the dot product. So the product here is just -1 times 3 plus 2 times 4, and we get -3 plus 8, or 5. Now we can also multiply B by A, but if we do, remember we always have to have a row matrix by a column matrix. So B by A will still look like 3, 4 by -1, 2. So we haven't changed the values of the vectors. B is still the 3, 4 vector, A is still the -1, 2 vector. We're just writing B as a row matrix and we're writing A as a column matrix, because that way we can take 3 times -1 plus 4 times 2, and we get -3 plus 8, or the value 5 that we're looking for. And what we see is that we come out with the same result each time. We come up with 5 when we take the dot product in the most traditional way, we come up with 5 here, and we come up with 5 here. If we instead had expressed these vectors as matrices and tried to multiply a column matrix by a row matrix, in other words, flipped the order here and put the column 3, 4 before the row -1, 2, then the result of that is a 2 by 2 matrix. That's not the dot product. Again, we'll talk much more about vector products later on, but right now we just want to understand the idea that this dot product is the sum of the product of each of the associated components of the vectors. And normally when we find it this first way, but if we want to express the vectors as matrices, we just have to remember to start with the row matrix and follow it up with the column matrix.